Good day, students. Here is lesson 4.1 on the basic concepts of probability. First of all, as we begin, we're going to go through some basic definitions, and then I'll talk about how we can analyze a claim, and we'll talk about basic definitions of probability. So let's get started, and we'll go from there. The first thing I want to talk about in basic concepts of probability is what is an event, what's a simple event, and what's a sample space. Okay. So an event is just the collection of outcomes of a procedure. So, for instance, if you're doing a medical experiment, you're testing a drug, and you have a blood test for cholesterol for everybody. So the outcomes of that event would be the cholesterol levels for each of the patients in the study. It could be you're checking babies that are being born to people and just recording the sex of those babies, whether they're a boy or a girl. And so the event would be whether a boy was born or whether a girl was born. All right. A simple event is an event where you can't break down the event to simpler parts. Okay. And then a sample space is essentially an event or the group of all simple events of an experiment. So a simple event is usually one item. So that would be one cholesterol result because you can't break it down to half a cholesterol report. Okay, or it would be one baby that's either a boy or a girl. It's a simple event. And then the sample space is the collection of all those simple events. Okay, and so probably the easiest way to understand it is would be like if you roll two die. Okay, if I roll two dice, okay, and what I want you to do is I want you to add the die and list the outcomes in the event. So the event is rolling two dice, and I list all the sums. Now, the simple events would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are all the simple events. Okay? Because I can't, when I roll a 2, I just get a 2. The sum is 2. It's a simple event. The sample space would then be the collection of all of these. Okay? And then an event could be it could be all of them. It could be just the even sums or just the odd sums or all the sums less than 6. Okay, so events just depend on the description. Simple events can't be broken down any further, and then the sample space is always the collection of all of them. Okay, alrighty, let's go on. So one of the things that I want to emphasize is that we need to use correct notation. So when we use the letter P, that stands for probability. And then we use other capital letters like A, B, C to represent specific events. Okay? That's a specific event. And so when we write the probability of A or the probability of B, what we are saying is I want to know the probability of this event. So let's go to our rolling dice example. So our rolling dice example, the sample space, which we'll call S, is equal to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay? That's our sample space. So let's let an event, we'll call event A, the set of outcomes less than 6. So that would be 2, 3, 4, and 5. And we'll let B be the set of outcomes that are odd. So 3, 5, 7, 9, and 11. And we could make lots of events, okay? The even numbers, the numbers greater than 6, the event of just 6, there are a lot of them. Now, if I want to find the probability of A, I just need to count the number of ways, or the number in event A, and I needed to divide it by the number in the sample space. All right? And so what does that mean? Well, probability of A then is going to be 4, because there are 4 numbers less than 6, and the number in the sample space is 11. And so the probability of obtaining a number less than 6, when you roll 2 die and add up the die, would be 4 out of 11. That would be one way to think about it. Okay? Now, but this is actually more layered than that, because when you start to think about it, you go, wait a second. To get a 2, there's only one way. Oh, to get a 3, I could get a 2 and a 1, or I could get a 1 and a 2, and there were 2 ways. And in fact, to get a 3, there were 3 ways. To get a 4, there were 4 ways. Wait, let me think about that. To get a 3, excuse me, I put 1 here. Sorry, that's 2. 3. To get a 4, there are 3 ways. To get a 5, there are 4 ways to get a 5. To get a 6, there are 5 ways to get a 6. And to get a 7, there are 6 ways to get a 7. And then it goes back down. 8, there'll be 5, 9, there'll be 4, 10, 3, 11, 2. So the reality is there are actually 36 outcomes. So this 4 over 11, when we think, oh, that if I just list these numbers, this would be true. But if I'm really talking about dice, there were 36 possible outcomes, okay? Because the way the dice show up could be different. There are, 6 ways you could get a 7. And so then when you look at this, it's not like just looking at the numbers in the list. It's looking at how many ways could you get that sum. And in that case, there's 1, 2, 2 3s, 3 4s, and 4 5s. So that's 1 plus 2 plus 3 plus 4, or 10 out of 36, which is 5/18. Okay? And so the point I'm making here is when you describe the sample space, okay, you have to understand the other underlying structure of that sample space. Otherwise, your probability statement is not going to be true. And so there was a structure here because there's more than one way to get almost all these sums, except for 2 and 12, because each die is different. Now, if I was just saying I have the numbers 2 through 12, then it's just a number, and then the 4 11s would have been correct. But if I'm really talking about die, I need to take into account the structure of the experiment. But in either case, this is what the probability is. It's always the number in the event over the number in the sample space. And so this is, in my mind, is what makes probability hard, is sometimes we don't understand the underlying structure. And so sometimes you have to really work through that. Okay, let's go to the next slide. I should mention your textbook talks about three approaches to probability. It talks about the relative frequency approach, relative frequency. It talks about the classical approach, and it talks about subjective. And so, what are the differences between these? The relative frequency approach is where you're kind of like insurance companies. They tend to look at how often do males under 25 crash cars versus females under 25 versus married males under 25 versus single males under 25, etc. And so they use those relative frequencies to figure out probabilities. Okay, so a relative frequency is a probability. Classical probability is where the outcomes are equally likely. This was more of a classical probability problem, where each die has a 1/6 probability of whatever shows up on its face, and then each sum then will have a probability based on the probabilities of what shows up on the faces. That's a very classical approach. And then a subjective probability is that, it's really based on kind of experience. What's the probability? I've been thinking about these airplane crashes that happened, 3 plane crashes in the last week. And what's the probability that you would be on an airplane crash? Well, there are thousands and thousands of flights every day. And so the probability is actually quite small that you would be in a crash. It still creates fear or uncomfortableness with flying, but that's sort of a subjective probability. It depends on the circumstances. All right, let's go on. So one of the things we do is we do simulations. A simulation would be where we use like random number generators or experiments to actually demonstrate what happened. So a simulation then is a situation where we, might use a random number generator to electronically flip coins or choose between two numbers, 1 and 2, that would imitate actually flipping a coin, so we don't have to do that. That does exist on the TI-84 calculator, although I don't know if it exists on our calculator at all. But we can actually, if you actually own a TI, you can do simulations on it. So, and that's kind of fun. It's sort of a good thing to be able to do. We're going to round probabilities. Typically, if we don't know what they exactly are and they come from some sort of fraction or decimal, we tend to round them off to 3 decimal places. Okay? 3 decimal places. And that'll be good enough for our experience. The textbook at this point gives some examples. So, a relative frequency probability, they actually use the airplane crash example in that there are thousands of flights, and how many crashes do you have every year, and that gives you a probability. And so, say in the last week there have been 10,000 flights, but there were 3 airplane crashes. then that probability would be 3 over 10,000. Okay. Classical probability, flipping coins, drawing cards from a deck, poker hands. Those are all examples of classical probability. Poker hands is probably the most common one you see when you see poker on TV or something like that, and they start flashing percentages. It's based on classical probability, and then subjective. The example they give in the book is what's the probability you'll earn an A in statistics class? Well, that's based on a lot of things. How much you study, how do you prepare, do you do the homework in a timely fashion, do you think about why on all your answers, etc. And then you assign a probability based on that. It's sort of like the kid who has his bike and he's doing going over a bike jump, and he just estimates, can I land this? And he takes off and then decides if he can land it or not. And he won't do it until he feels like he has a good chance of doing that. So a high probability of success. All right, let's go on. Okay, so let's talk about the rare event rule. And there it is, the rare event rule. If, under a given assumption, the probability of a particular event is very small and the observed event occurs significantly less or significantly greater than what we typically expect with that assumption, we conclude the assumption is probably not correct. Okay, so in a medical study, all right, let's just go with a medical study. If you have a medical study and they give you a drug, okay, then the assumption is the drug will not work. That's the assumption, okay? And so if it's a weight loss drug or something like that, if you take this drug and then you lose lots of weight, say in a year you lose 30 pounds, all right, that would be significantly greater than what we would expect. But if you only lost, say, 2 or 3 pounds in that year, then nothing's really changed. You're still essentially the same weight you were when you began. Okay? So in the second case, we assume the assumption that the drug would work. It doesn't work because no weight was really gained or lost. All right? And so that would be, we would then assume that our hope for that drug, that it would help you lose weight, would be less than we hope. On the other hand, if you lost 30 pounds, then we would assume that our assumption that the drug does not help would be wrong, and so that would be significant. So that's kind of what happens in a medical study. You sort of assume status quo, and then you see if the drug changes things significantly, greater or less, depending upon what you're doing. All right? Your textbook writes this down on page 152. And I would definitely go into that page where it talks about a significantly high number of successes or a significantly low number of successes. They give 2 examples. Among 20 births, 20 girls is significantly high because the probability of 20 or more girls is like 9 1/millionths, right? Which is less than or equal to 0.05. So the gender selection would appear effective. Among 20 births, 12 girls is not significantly high because the probability of 12 or more girls is 25%, which is bigger than 0.05. And we tend to use 0.05 as the borderline of being significant or not. Okay? Now, probabilities are always between probabilities. If we kind of make our notation, the probability of any event will be between 0 and 1. Okay? If it's an impossible event, if the probability of an event equals 0, that's called impossible. In other words, it can never happen. All right. If the probability of the event is equal to 1, it's called certain. It will always happen. All right. And then we have the probability of the event and the probability of not the event. So we'll put this. The probability of not the event is 1 minus the probability of the event. Okay? So that's sort of our summary up to now. So our text does talk about something called odds. Okay, what are odds? That would be like the odds.
Can you open that jar for me, please?
Okay, sorry about that. Got a phone call. All right. So what are odds? There are a couple of odds. All right. And this shows up in betting, like horses or 50 to 1 or 5 to 1 or football betting. All kinds of betting has odds with it. So how are odds figured out? Well, what you have are a few things. You have what's called the odds against, the odds in favor, and then you have the odds, the payoff odds. So, okay. And so the odds against are actually defined as the probability of an event not occurring over the probability of the event. Okay. The odds in favor are the reciprocal of that. And the payoff odds are always the ratio of the net profit. So it's the net profit to the amount you bet. That's the payoff odds. Okay? And so let's look at a quick problem. Okay. So I just decided I'll do the odds problem in a little bit. I've given you the definitions. What I'm going to do now is I'm going to do some probability problems, and then I'll do some odds problems. So let's go to the next page and do some problems. So I'm going to grab some problems from your textbook, just different ones. Here's an interesting one. This is 3A. It says, find the probability that when a single 6-sided die is rolled, the outcome is 5. So we're rolling one die, and we ask ourselves, we want the outcome to be 5. So since it's just one, to get a 5, that's our event, all right? And then the sample space is, we could get a 1, 2, 3, 4, 5, or a 6 if we roll one die. And each of these has an equal probability, okay, of 1/6, because there are only 6 outcomes. So the probability of get a 5 on roll of one die is equal to the probability of the event, probability of 5, or excuse me, not probability, the number in the event over the number in the sample space. And we see that there is one way to get a 5, and there are 6 possible outcomes, so that probability is 1/6. Now, when you start doing your homework, You should probably start writing things like this on your paper. Don't just fall back into the I do things in my head. Think how many are in the event, how many are in the sample space. Even when you have easy problems, try and start writing that down. So, and a student who writes this down and then writes this down, I know they understand the problem. Okay? And that makes a difference on a test. Okay? Another example, 3C. 3C, they want the probability that the outcome is a 7 when you roll one die. So again, our event is we get a 7. Our sample space is 1, 2, 3, 4, 5, and 6. And so the probability of getting a 7 is equal to the number in the event, which is 0. So our event, this is impossible. I probably shouldn't have wrote it like that. This is impossible event because I can't get a 7 when I roll a 6-sided die. Okay, so it's probably better for me just to write impossible here. Okay, and then now I know that the number in there is 0 over the number in the sample space, and 0 over 6 is 0. So this is an impossible event. Okay, and you could have even just said that. This is an impossible event since the sample space is this, and therefore the probability is 0. A number of ways you could have said it. All right, let's look at another problem. So the survey said 17% do not carry cash. So the probability of no cash, I'll call it that, is going to equal 17%. Okay? And that's what I would write down. And then it says, does it appear that most adults carry some cash? And I would say yes, since the probability of carrying cash is 83%. Now, another problem you could get from this is you could ask yourself, how many adults would you expect to carry cash? All right. And so, or how many adults would you expect to have no cash? So since you would say 17% is the probability of not carrying cash, you could then say 17% of 3,000, all right, which if you multiply that out is equal to 510. So you would say, so I would expect approximately 510 adults to not have cash. So you could actually move away from a probability statement to a numerical statement. Now, suppose you were performing a test here. Let's do the rare event rule. And suppose from many surveys, this is what we find out about no cash. And suppose then I take a random sample of adults, all right, but I end up with 1,500 of those adults are not carrying cash, okay? This would be an unusual result. This would be significantly different than that, right? 3 times larger a percentage. So it may have some statistical significance, and I might want to reject my assumption that 17% don't carry cash, that maybe the percent is much larger. Okay? And so that's kind of how the rare event rule works. If this is sort of the accepted norm, and then you take a sample of 3,000, but you get 3 times what you would expect, then that's a different issue. Okay? Let's look at some more. Okay, so another type of problem that you'll see is probability from a sample space. So suppose we want to find probabilities, and this is like problems 29 through 32. Okay, it's like those. Suppose I want to find probabilities for having children. Okay, and so one thing I can use sometimes when I'm doing things is I can use a tree diagram. So, for instance, there's a first child and a second child. Say a couple has two children. Okay, so what are the probabilities of the situations? Well, the first child, they could have a boy or a girl. All right. If they have a boy, their second child could be a boy or a girl. If they had a girl, their second child could be a boy or a girl. Therefore, the outcomes, so the whole sample space, all right, would be the set of either they had a boy and then a boy, they had a boy and then a girl, they had a girl and then a boy, or they had a girl and a girl. And that would be the whole sample space, the set of all outcomes. Now, you could make several events. Like one event could be the set of having one girl, all right? The event of having one girl. So that could be either a boy or a girl or a boy. Now, this way of thinking about setting up probability problems is really good using the tree diagram, because then we can find the probabilities of the outcomes as well. If you think about it, there's a 50% or a 1/2 probability for having a boy or a girl at any specific time. So the second time around, it's still 1/2 for each individual situation. Okay. However, we'll learn this in the next chapter, the probabilities overall. There's something called the multiplication rule of probability. And you would think then we see that having a boy and a boy, or a boy and a girl, or a girl and a girl, or a girl and a boy, that the probability of those is 1/4. That a couple would have a 1 in 4 chance of having either of these things happen. Now, basically, that's multiplying down a branch. So we're going to see that later in some other sections on probability. But I just want you to see that saying having a girl and a girl would be a 1/4 probability. On the other hand, having a boy and a girl and a girl and a boy, having just one girl, would be a 1/4 probability for this situation and a 1/4 for that. So you would add those together to get 2/4, or you'd have a 50% chance of having just one girl. All right. And so these are kind of ways you can think about problems. Your goal, mostly for this section, is to be able to write sample spaces and write events using some sort of notation so you can see the difference. A lot of times you'll see this as male, female as well. Or for coins, heads and tails. Or cards, getting a heart and not getting a heart, not a heart. All right. And so you can create sample spaces in this way very easily. All right. So there are problems like that. All right. And so for like our last example, I think what we want to do is we would like to talk about probability and significance. All right. And they have a great problem 33. And it says this. It says a county clerk in New Jersey was supposed to use randomness to assign the order in which candidates' names appeared on the voting ballot. Okay, so if you use randomness, what you would expect, if you had 2 candidates or 10 candidates, you would expect on the ballots the number of times a candidate showed up at the top of the ballot would be the same. Now, just for posterity here, let's just say Democrat, Republican, Independent. And it could be Smith, Jones, and Johnson could be their names. All right, so either way is fine. But suppose we had 3 candidates. Now, suppose in problem 33, they randomly pulled like 50 ballots. Okay, they said 41 in the problem, but they randomly pull 50 ballots. Okay, and what they noticed is that 49 out of those 50 ballots had the Republican listed first. All right. And then the Democrat and the Independent were maybe randomly switched around. But 49 out of the 50 had the Republican listed first. Now, if that's something that happened, the probability of this happening, if you have a real random process to put people on the ballots, is very, very low. Okay? Way lower than just, that would happen only 1 out of 50 times. No, it's a 1/3 probability because you got a 1/3 chance of being selected, 1 out of 3, to the 49th power. So it's like super small. All right, you go ahead and figure that out on a calculator. It's really, really small probability. So if randomness was used, we would have expected them to be there 33% of the time. But we got a super small probability so that what happened actually happened. Okay, so that would indicate to us by the method of this section, which is, let me say it again. Yeah. The law of large numbers says any procedure repeated again and again will have the same probability as the actual probability. It'll approach that. And so if we did this 50 times, that 50 is a pretty big number, but we would expect about 33% of them. It might be 30 and 36 and 33, but we would expect it to be close to 33. And so if it turns out that it's like 0.00001%, it's really small, then we have a situation where something wrong has happened. Okay? And not something wrong, but something significant has happened. That's the key word. The key word is the word significant. Okay? And if something significant happens, then what we need to do is apply the rare event rule. Okay? So we had a significantly high number of Republicans. Okay? And so that is that's really unlikely to happen. Therefore, we would conclude that the assumption that the candidates were applied randomly is false, and that's sort of the issue. That's how you work with it. Okay. So the law of large numbers tells us this should be 33% or close to it, but we ended up getting, 0.0001%. And so that's significantly different. And so therefore, we would conclude our assumption that they were assigned randomly to the ballot is incorrect. Okay, that's all I have for you today. Good luck. Talk to you later.